Hi, and welcome to Triple Integrals. In our introduction to multiple integrals, we saw how triple integrals look like. We know that we have three integral symbols. That's the triple integral symbol. In front of it, we have the integrand f, which is a function of three variables. And in front of it, we have the differential volume dv. Underneath the triple integral symbol, we have the letter d, which represents the region of integration. So it's very similar to double integral, but there are three differences. First is the integrand. The integrand here is a function of three variables, but the integrand in double integral was a function of two variables. Next is the differential volume. dv is different from dA, which was the differential area. Finally, the region of integration d here is a 3D region. In double integrals, we use the letter r because the region of integration was a 2D region. Let us now try to make sense out of triple integrals. Because functions of three variables already use all three dimensions in their domain, we cannot graph them in 3 dimensions. We need 4 dimensions to graph them. Because of that, as humans, most of us will have difficulty imagining their graphs and will have no choice but to just settle for the region of integration D instead. Because of this, our main tool for making sense out of integrals, the geometry, isn't there anymore. There is no geometric interpretation for the triple integral of a function. But that's fine. Our analytic tool, the Riemann sum, is still there. We're going to use Riemann sums as before. What we do is we divide the region of integration into tiny rectangular boxes, like the red one shown in the figure. And then we assume that the function f is constant along each of these tiny boxes, and we will have our Riemann sum. In this case, it will be 3 nested sums. And of course, at infinity, at differential length, these nested sums become 3 nested integrals. Before we get into the evaluation of triple integrals, let us see what other parallels we can draw between triple and double integrals. The first scenario is the case where the integrand is 1. In double integrals, we saw that if we integrate 1 over a two-dimensional region R, we get the area of R. We have the same scenario here. If we integrate 1 over some 3D region D, we get the volume of D. Next is the physical interpretation. To explain this, let us go back to single variable integrals. We already know that the integral of a single variable function over some interval is the area underneath the graph and above the x-axis. Well, if the axes in question are marked with the right physical quantities, then this area will also have a nice physical interpretation. For example, if the x-axis is displacement and the y-axis is force, then this area gives us work. Well, it's true that we do not have a geometric interpretation for the triple integral, but we still have the physical interpretation if our integrand is the right physical quantity. For instance, if we are integrating density over some region D, then the value of the triple integral will be the mass of D. Another thing that's common between double and triple integrals is the average value. We saw that in order to find the average value of a function over a two-dimensional region, all we have to do is to calculate the double integral of that function and then divide it by the double integral of 1 over that region. Well, we have the same exact thing here. In order to find the average value of a function over a 3D region, we calculate the triple integral of that function over that 3D region and then divide it by the triple integral of 1 over that 3D region. So that's it for our general discussion of the triple integral. We covered almost all the topics that we had covered for double integrals. The only thing that we did not discuss, which is of course the most important question, and that is how do we evaluate a triple integral? This question we will answer in the remaining videos in the course.